Today we will be discussing about the MOSFET circuit under DC. So, when we apply a DC voltage between the gate and source, then what will happen? The currents in the different branches can be found out. So, that DC operation we will be taking up today. Now, in the last classes we have discussed about the different types of MOSFET. We have discussed about the enhancement type, depletion type, and in the enhancement and the depletion type MOSFETs there are two types again, that is N channel and P channel. So, in our discussion today we will be taking examples of both these MOSFETs and try to solve examples dealing with the DC operation. For example, let us take one circuit. Here we are having a MOSFET. By the symbol of the MOSFET we know what type of a MOSFET it is. So, this MOSFET is N channel depletion type MOSFET. So, the voltage at the drain is denoted as VDS because S is the source which is grounded. So, VDS is also represented by VD because source is grounded. A 20 volt supply is there and a resistance 1.5 kilo ohm is connected between the voltage and the drain terminal, and here the gate terminal is shorted to the source. Now, we are asked to find out the VDS, that is what will be the voltage between the drain and source, that is to be found out. Now, given that IDSS is equal to 10 milliampere and we know what is IDSS, that is the drain current or drain to source current when the voltage between gate and source is 0. So, this is a value which is specified in the data sheet for a particular depletion type of MOSFET. So, for this example we are having IDSS value as 10 milliampere. Also specified is that the MOSFET device has a threshold voltage minus 4 volt. So, we have to find out VDS. So, in order to find out the drain to source voltage, we have to solve the circuit. So, in this circuit which is again drawn, we are denoting the drain current by ID, that is the drain to source current. And one thing to be noted is that the gate terminal is connected to source as a short circuit and the source is grounded. So, if we now apply the Kirchhoff's voltage law to this circuit, because as we know that this circuit can be solved using the typical laws of electrical engineering like Kirchhoff's voltage law, Kirchhoff's current law, etc. So, we will be applying Kirchhoff's voltage law in the loop from the end of the 20 volt supply voltage. If we travel downwards to ground, because it will be completing one loop starting from here to ground. So, traveling along this path, if we apply now the Kirchhoff's voltage law, what will it be? It will be equal to V 20 volt minus ID into 1.5 kilo ohm minus VDS is equal to 0. Now, you have to look into this circuit. Here we are having VGS equal to 0, because the circuit itself shows that the voltage between the gate to source is 0. So, VGS 0. So, that is why the drain to source current is the specified IDSS. So, for this particular circuit, as we are having the gate to source voltage 0, so the current between the drain and the source is the specified IDSS, which is given as 10 milliampere. So, we can now find out VDS, the drain to source voltage, or simply we can write it as VD. VD or VDS, this is the same thing because the source is grounded. So, the voltage between drain and source is nothing but the voltage between the drain and the ground. So, it is very simple to find out this voltage VDS or VD, which is nothing but 20 minus this drop, and this drop is IDSS into 1.5 K. So, that if we calculate replacing the value of the current, which is 10 milliampere for this particular MOSFET, we are given that IDSS is equal to 10 milliampere. So, this calculation yields a voltage of 5 volt. So, 20 minus 15 is 5 volt. So, that means the voltage at the drain end with respect to the source or ground is 5 volt. This circuit or example is employing the depletion type MOSFET having N channel, that is we are using an N channel depletion type MOSFET, which is very clear from this symbol of the MOSFET. Now, let us try another example which is given in the circuit shown in the figure. Here you have to design the circuit as shown in figure 2, so that the transistor operates at ID drain current is equal to 0.4 milliampere and VD is equal to 1 volt. The MOSFET has the threshold voltage VT is equal to 2 volt and it is in saturation. Now, given the value of K is equal to 0.4 into 10 to the power minus 3 ampere per volt square. So, here this point is important, that the MOSFET is in saturation. So, as it is in saturation, we have to consider that the voltage VD must be greater than VGS minus VT, and the threshold voltage is given as 2 volt. So, we will be finding out VGS corresponding to that condition of saturation. So, writing down the relation of the ID current with respect to VGS and VT, which is this nonlinear expression, we will be finding out VGS, and this quadratic equation gives two solutions, but out of these two solutions only one solution will be feasible, which will be satisfying the condition for saturation, that VD must be greater than VGS minus VT. So, we will be now solving this quadratic equation and find out that value of VGS. After simplification we get this and this cancel 0.4, 0.4. So, it will be 1 equal to VGS minus 2 whole square. We get an equation 1 equal to VGS minus 2 whole square. So, simplifying this we get VGS square minus 4 VGS plus 4 equal to 1. That gives us VGS square minus 4 VGS plus 3 equal to 0. So, we need to solve this equation for finding out the gate to source voltage for this circuit to be under saturation. So, now for the on condition we have to find out what is the VGS. Now, this equation is a quadratic equation, as we see it will be having obviously two values of VGS. So, if we solve this equation it will be VGS equal to 4 plus minus under root 16 minus 12 divided by 2. So, what will it be? It is 4 plus minus 2 by 2. So, basically we get 6 by 2 and 2 by 2. That means we have two values, 3 volt and 1 volt. But if we have VGS is equal to 1 volt, then our condition that VGS minus V threshold must be less than VDS. That condition will not be satisfied, because VGS minus VT will be then how much? 1 minus VT we have been given as 2 volt. So, 1 minus 2 means it will be minus 1, but we have VDS is equal to 1 volt plus 1 volt. So, this is ruled out. Now, if VGS is equal to 3 volt, this condition is met, that is VDS is greater than equal to VGS minus VT. That will be met when this is 3 volt. So, VGS is equal to 3 volt is the critical condition which will be making the circuit to be under saturation. So, we will be taking that value of VGS which is equal to 3 volt. Now, with this VGS equal to 3 volt, we will be now proceeding to find out the resistances. So, in this circuit we now solve in the output circuit VDD minus IDRD minus VD equal to 0. VD means with respect to ground. Now, VD has been given to us as 1 volt. So, putting down the values of this VDD and ID, we can find out what is RD, because others are known except for only RD. So, VDD is equal to 5 volt. So, 5 minus ID given to us as 0.4 milliampere. Keeping that as 0.4 only, then the answer will be in kilo ohm, minus VD is equal to 1 volt, the voltage at the drain end is 1 volt. So, this gives us the solution of RD equal to 10 kilo ohm. If we solve this equation, it will be 10 kilo ohm. So, we know what is RD. Now, what will be RS? So, RS, in order to find out RS, we will be coming through the bottom loop. So, this is 0 minus VGS, this is VGS between this drain and gate, this is drain, this is gate, this is source. So, with respect to source terminal, this voltage is VGS. So, this is ground point. So, we will be going through this loop 0 minus VGS minus ID into RS minus VSS is equal to 0. So, applying KVL, in the bottom loop, we get this equation. Now, VGS has been found to be equal to 3 volt and ID also known, VSS is minus 5 volt. So, we will be now solving this equation, only unknown is RS. So, RS is equal to 5 kilo ohm. So, for this circuit we have found out the two resistances RD and RS. So, in this way the operation of this MOSFET device when only DC voltages are there is illustrated in these two examples. Now, why do we use a MOSFET device, or for what applications we use a MOSFET device? We use MOSFET for amplification. Now, earlier when we were discussing BJT, bipolar junction transistor, we have studied about the application of the BJT as amplifier. So, we have seen how amplification of a weak signal takes place. Now, similarly, a MOSFET device also is used as an amplifier. So, now we will be studying about the use of MOSFET as an amplifier. So, if we now take for example a simple circuit to illustrate how a MOSFET device is used for amplification, let us now take this circuit having an enhancement type of MOSFET device. We are restricting our use to enhancement type MOSFET in this particular discussion, but we have depletion type MOSFET also which is used as amplifier, but as we are going to discuss about the basic amplification and other related matters, so we will be taking up the example of enhancement type MOSFET and we will be discussing other aspects related to amplification. Instead of discussing different type of MOSFET devices, let us concentrate on the application of enhancement type and see how the amplification and other related things can be understood. It is not necessary that only enhancement type of MOSFET device will be used for amplification, but we are taking this example. The amplification and biasing etc. can be also explained for depletion type of MOSFET etc., but we will be discussing one particular type of MOSFET and focusing on it. So, we are taking an N channel enhancement type of MOSFET. Now, what is the amplification? We already know from our earlier studies that amplification means we are trying to increase or enhance the magnitude of an weak signal without distorting its shape. So, if we have a small or a weak signal, we will be using an amplifier so that at the output we get an amplified form of the input signal. The shape of the input signal should not vary. We need or we desire faithful amplification, but obviously its magnitude will be enhanced. So, that is the basic principle for amplification. So, similarly, as we were discussing in BJT, the concept of amplification is similar for this MOSFET device also. We will be proceeding in a similar way. So, here we are having this MOSFET, which is an N channel enhancement type MOSFET. In our study we are taking that as an example. So, we are having DC sources as well. We are also having a small signal, so that we finally get an amplified form of this weak signal. Our aim is to amplify the small signal. Now, between the gate and source, this is the gate terminal, this is the source, this is the drain. So, this amplifier is amplifying a signal between gate to source, which is small v gs. Apart from this signal, there are DC sources there which are needed for biasing. We will be discussing about the biasing schemes later, but in general this figure typically shows one arrangement for amplifying a small signal. Now, the gate to source voltage is, if it is varied, we know the drain current, the drain to source current will vary. Now, we have earlier studied about the transfer characteristic and the VI characteristic also, and we have seen there are three different regions of operation. One is the cutoff region, one is the triode amplifier region, and the other is the saturation region. For saturation region, the condition to be satisfied is that the drain to source voltage must be greater than VGS minus V threshold. Now, in this circuit, let us show the drain current as ID. Now, one important thing to note is that here a combination of both small as well as a capital letter is used, just to signify the instantaneous value of voltage and current. We use both the small as well as the capital symbol, because we have two situations here, one is the DC, one is the AC. So, the DC condition is for biasing and the AC condition is for the signal. So, if we do not have the signal, as we have earlier discussed in the examples which we did just now, if we have only DC quantities or DC voltages and currents, if we have only DC situation, then we denote the voltage and current by capital letter, say VD, ID, etc. And if we purely have AC signal, we denote the signal by small v small d, small I small d, like this. Now, we are having both DC and AC conditions. So, what we will be having? We will be having a superimposition of AC on DC, that is, In absence of the AC signal, we will be having a constant DC voltage, say Vd, or if we consider the gate to source voltage, we have VGS, which is a DC signal, DC voltage. If we now apply this AC signal small v small gs, we will be having on this DC voltage a superimposed AC voltage like this, small v small gs. Now, at any instant, if we consider the total voltage between gate and source, suppose at this instant what will be the voltage? It will be this total voltage, which is having a DC part and an AC part. To know that, or to express that instantaneous value of this voltage, we use the symbol small v capital Gs. Similarly, the current component also, if we consider, if we have only the gate to source DC value of voltage, which is capital V Gs, then corresponding drain current is, say, capital I capital D, and when we have the signal applied small v small gs, the corresponding current in the drain is small I small d. Then with both of them being applied, VGS plus small VGS as is shown in this figure, we have corresponding drain current as capital I capital D plus small I small d, and this quantity is denoted by small I capital D. So, that is here this shown as in this figure. So, this small I capital D actually means combination of DC current as well as the AC current, DC ID and AC ID. Now, when we want to do amplification, that means if we have a small signal here at the drain end, we will have to get a amplified signal. Now, the voltage at the drain end with respect to ground is small v capital D. So, by that also we are meaning instantaneous voltage, which is a combination of both DC and AC. So, this circuit is actually a very simplified version to actually understand the amplification. In practice, we may not get such a simple circuit, but for understanding purpose, we are taking it in as simple manner as like this, but in actual, while we will be discussing about biasing etc., we will be having a complicated or a different version than this particular small circuit, but for the time being we will be considering a smaller circuit or a simpler circuit for first of all understanding the basics behind the amplification. So, at this point we are having a combination of both DC and AC, as it is not having any capacitor etc. to block the DC component. So, we are having both the DC and AC being present here. Now, one important thing to understand or to remember before going to discuss the amplifier in details is that to operate as an amplifier, the MOSFET device must be biased in the saturation region. This is an important thing to note, and always remember is that we will be operating the MOSFET in saturation when you want to apply it as an amplifier. It is just like when we were considering the BJT in amplification or as an amplifier, we know that we operated the transistor in the linear region, that is in the active region. So, the first and foremost condition which has to be met when a transistor BJT is operated as an amplifier is that the BJT must be operated in active region. Similarly, the MOSFET must be operating, or it must be in saturation condition to work as an amplifier. So, that condition has to be always satisfied, that VDS is greater than VGS minus VT, so that the MOSFET is under saturation. So, here what we are doing, we are varying the gate to source voltage VGS. This is the controlling quantity. This is the controlling quantity, as in BJT we were controlling by means of the base current, we were controlling the collector current by means of the base current. Here we will be controlling the gate to source voltage and controlling the drain current ID. So, this is the idea which will be applied in amplification, that is we have to control VGS to control ID. Now, in order to study the amplifier in details, we will be considering the DC and AC conditions separately, because what we have done in BJT also, that we were considering the DC biasing condition, and then we were considering when the signal was applied, and then we were combining both of them. So, we want to analyze the DC condition, and then we will be going to the small signal model of the MOSFET device, so that we can analyze it for being used as an amplifier to know the parameters. But before that, let us now see what will be the condition when you do not have the signal, only have the DC condition. In this particular example, if we first of all do not have the signal, without the signal, only purely DC condition is prevailing, then the circuit will be having the DC voltages VGS and VDD, and the small VGS is absent. In the absence of small VGS, we are having this circuit. So, the current which will be flowing in the drain, or from drain to source, is capital I, capital D now. Now, without signal, if we find out the drain current capital I, capital D, we know that this is an enhancement type of MOSFET, and the relationship for the current and voltage is given by ID equal to K into VGS minus VT whole square. This expression we will have to always keep in mind. Now, again, what is this voltage? Now, we note that this is a DC voltage. We are having the DC condition only. So, this capital V, capital D signifies or denotes the DC voltage only. So, what is VD? We can apply Kirchhoff's voltage law directly. VDD minus capital I, capital D into RD equal to VD. So, this is as simple as that, because we are not having the signal, we are having only DC condition. So, we are analyzing the DC circuit, and as the amplifier has to be in saturation, so at any point during operation it must be satisfying the condition for saturation. So, VD must be greater than VGS minus VT. Now, we are applying a signal also, that has to be kept in mind. So, when you apply the signal, your Vd, whatever you will be getting at the drain end, that voltage should be such that at no point the condition for saturation is violated. That is because we are having a signal swing, because of the swing in the input AC voltage, this is VGS. So, if we have a DC VGS here, because of the signal, we will be having the drain current small I small d superimposed on the capital A capital D, which is due to VGS only. So, for only application of capital V, capital G, capital S, that means the DC VGS, suppose we have a VD S as this one, that is VDS, capital V capital DS means it is the DC voltage due to this VGS only. Because of this application of this signal, we have a small I small d. So, due to this small I small d, we will be having a corresponding small v small d. So, this will be coming on it. So, at no point of time the VDS or VD must be less than this quantity. So, that has to be kept in mind, because we are dealing with amplification, we know that the output voltage will be greater, it will be having a high magnitude. So, the biasing should be proper there, so that under no condition this is violated. As we have seen in BJT, at no point it should go to cutoff or saturation, it should be always in the active region, so that the input is forward bias, the emitter base junction is forward bias and collector base junction is reverse bias, that has to be maintained always. Similarly, in MOSFET, this condition has to be satisfied for enhancement type of MOSFET we are dealing with, so that it is always in the saturation region, because the MOSFET amplifier operates in saturation region. Now, without the signal we have discussed, the DC conditions we have got. Now, if this signal is applied now, what will happen is that we will be having a current at the drain, which is denoted by small I capital D, because small I capital D means it is DC plus AC. So, now total instantaneous gate to source voltage when we have the signal along with the DC signal VGS equal to capital V, capital G, capital S plus small v GS. So, this is the total instantaneous gate to source voltage. Now, due to this gate to source voltage, we have the drain current, which is denoted by small I capital D, meaning that we are having both DC and AC. Now, that is given by the current law. The current law is what? That is equal to ID equal to K VGS minus VT whole square. Now, this is if we have the DC condition. Now, we are not having DC condition because we are having the DC and AC both. So, the instantaneous value of the drain current, if we want to find, then the total voltage between gate to source we have to take care of, and that voltage is capital VGS plus small VGS. So, instead of this VGS, we will have to put capital VGS plus small VGS minus V threshold, that is specific for a particular MOSFET device, which is given in the data sheet itself. So, now our relation for the current is this one. So, instead of only VGS, we are having this voltage, and this Kn, it is the fabrication constant for the n channel MOSFET enhancement type of MOSFET, and this is basically a constant which is given or which can be computed given the parameters like length of the channel, width of the channel, etc. So, in this particular discussion we are using it as a constant instead of going into the computation of Kn. Let us keep that in mind, that we are using a value for the constant which we are assuming as known. Basically, the way to find out the value for K also is another topic. We can find this out provided we know about certain other parameters like length, width of the channel, mu n, etc. But we do not go into those details, but let us assume that we already know or it is given to us in the data sheet. So, now if we now expand this current expression, in the right side it is a plus b whole square type of quantity. So, just if we want to break up a square plus twice ab plus b square kind of expression we will be getting. So, that is equal to Kn into, let us keep VGS minus VT together. See, this whole thing under the bracket is VGS plus small VGS minus VT, but let us take the quantities VGS minus VT together and small VGS separately. So, that will be now expanded as a square. So, it is a square plus twice a into b plus b square. Now, if we closely look into this whole expression, first expression Kn into VGS minus VT whole square, that is nothing but the DC biasing current, capital I capital D, because if we look into the quantities, this is the DC quantity of the gate to source voltage and this is the threshold voltage. So, this whole quantity is nothing but the DC drain current. Now, last term in this expression Kn VGS square. Now, you see that this is a square term, small VGS, that is the signal. Now, this square means it actually is introducing a non-linearity. Because it is a square term, it will be a non-linear term. So, it will be causing distortion. In the whole current expression, if we have a non-linear term like this one, last one, which will be causing a distortion in the current. So, we have to reduce the effect of this distortion by this non-linear term, and that we can do if we choose the term carefully. That means, in comparison with this term, we have to suppose neglect this Kn VGS square. So, then what we will be doing, we will be making the VGS term or the small signal VGS so small that the square of that small term, which is again further smaller, and it should be very, very small as compared to the other term, which is this one. That means, we are now focusing on these two terms, because we do not want the nonlinear distortion which is introduced by this square of the VGS term, we want to get rid of this. That means this should be very, very small so that we can neglect it in comparison with this one. So that this plus this will be almost equal to this. So that this term should be neglected. Now, when can we neglect it? If it is so small in comparison with this other term, then only we can neglect. So that means what? We must make, or we must choose this VCS sufficiently small. It is sufficiently, it should be small so that if it is very small, its square will be obviously further smaller, will be smaller term. So, Kn VGS square is so small that it, in comparison with the other term twice Kn VGS minus Vt into Vs, or if we simplify a little further, it boils down to VGS is less than equal to twice VGS minus Vt, because this and this cancel and this square term and this term cancel. So, finally, we get a condition that VGS is very, very less as compared to twice into VGS minus Vt. So, then if this small condition, a small signal condition is satisfied, then we can neglect the term Kn VGS square. So, this is an important condition which we will be keeping in mind, that if the signal which we want to amplify, it is very, very less as compared to the right hand side expression 2 times capital VGS minus Vt, then the distortion effect can be neglected, or it is not causing distortion to the drain current. So, then small I capital D, or the instantaneous value of the drain current, is equal to the original expression. If we now again write down and ignore the Kn VGS square term, then we get this is the expression for the drain current. So, what is this current? The drain to source current, whose instantaneous value is small I capital D, and that is equal to, first term is capital I capital D, that is the DC drain current, and the second term is the AC term small I small d, where the small I small d is representing this whole term twice Kn into VGS minus Vt into small VGS. So, now if we do a one step further, that find out the ratio between small id and small VGS. If we find this, that is equal to twice Kn VGS minus Vt, and that signifies an important parameter which is known as the MOSFET transconductance, which is denoted by small z small m. So, the MOSFET transconductance small g small m is given by small I small d by small VGS, which is equal to twice Kn capital VGS minus Vt, where this Kn is of course the fabrication constant for the MOSFET device, and this is the DC gate to source voltage, and the Vt is the threshold voltage which is known. So, by transconductance we know a very important parameter for the MOSFET under operation, or the MOSFET device which we are using. That transconductance is equal to this right hand term, which actually characterizes the MOSFET. This will be very important when we go to discuss about the amplifier small signal model. So, now if we see the characteristic between the drain current and the gate to source voltage, which is nothing but the transfer characteristic. We are familiar with the transfer characteristic, which is a nonlinear curve which can be drawn if we know certain points by combining or by joining the points. We can draw a nonlinear curve. Of course, the starting point will be the threshold voltage when the current is 0, and some other points, 3 points or 4 points will be necessary to draw this transfer characteristic, and this is the say operating point Q. The operating point will be fixed by the biasing circuit, and that we are going to discuss very soon. So, if we have the operating point denoted by Q, then this is having the coordinates VGS and ID, both are capital to denote the DC condition. So, for a VGS, the corresponding ID is shown here, and the slope of this transfer characteristic at the operating point, which is ID by small VGS, that is actually the transconductance. So, from the transfer characteristic and operating point by finding the slope at the operating point, we can know the transconductance. So, in today's circuit, we have started discussing about the MOSFET as an amplifier. So, basically the MOSFET device is used for amplification of a weak signal by controlling the gate to source voltage, and the MOSFET device must be under saturation to be used as an amplifier. That is one very important condition, and we will be having the normal biasing arrangements for fixing the operating point, and then we will be applying a small weak signal between the gate and source to amplify it at the output end or the drain end. So, basically we will be getting a voltage at the drain which will be in an amplified form, but we do not want distortion of the input signal which is applied at the gate to source terminal. So, we will be later on discussing about details of amplifier circuits.